So, hello everyone. I'm Gitanjali. I'm a PhD scholar from IIT Delhi, and I'm a PMRF TA for this course, which is Introduction to Laser, taught by Professor Matsune from IIT Delhi. So, this will be our last live session of for this course, and it's gone through as we have done in our previous session. We'll go through the concept of the week 12, and I will solve few additional problems besides assignment, so that it will help you to for problem solving as well as in clarifying your doubts. So before starting the session, let me ask whether you have any doubt in the week 12 assignment. If you have any doubt in the week 12 assignment, then I will clarify the doubt now. Then we'll go through the remaining concept of week 12, and besides we'll solve few additional problem related to week 12. So please feel free to write in the chat box during the live session, or you can also unmute yourself to ask your doubt. I have unmuted everyone, so you will be able to speak if you unmute yourself. Okay, in the meantime, if you have any doubt, please write in the chat box uh, or unmute yourself. So let me go through the remaining concept of week 12, then we'll solve the problems that is related to week 12. So we're looking the lasers, how lasers can be used for nonlinear optics. So basically, we have seen for non-linearity by the term non-linearity, we mean the polarization of the medium. It has a non-linear dependence on the electric field associated with the propagating wave. So normally, whenever let's say we have a material, then if it is a linear material, then this is the general expression for the displacement current. So this is valid for both non-linear and linear material. So D is epsilon E, and epsilon E you can write it as a two terms. One is epsilon E, and one is the term due to the polarization that is induced in the medium in the presence of the electric field. So whenever you put electric field, external electric field to a material, so it will polarize because of the charges that is present in the material. So this term, the polarization, it is due to the external electric field. And when the electric field is small, so by small, what we mean? By small, we mean the electric field magnitude, it is small compared to the interatomic electric field. So this is what we mean by the small definition of this electric field in terms of nonlinearity. Okay. So for small electric field, we have polarization, which is directly proportional to the electric field, or you can write it as P equal to epsilon chi into E for linear material. So let us see how this electric field comes into the picture. So let us take one monochromatic wave. So the wave is a single frequency, which is given by omega. So you can write this expression. Please remember this small expression because these are crucial to solve the problem. So for monochromatic electromagnetic wave, we have electric field, which is equal to E0 cos omega t minus kz. And the instantaneous electric field at point Z, let's say you are taking Z equal to 0, then this will be given by E equal to E0 cos omega t. And when we have polarization in the medium in the presence of this small electric field, we can write P equal to epsilon chi into E. This is for the linear expression. This is the linear part. And chi, it is the susceptibility, which is, it may be a tensor scalar for the linear medium, but when you consider the nonlinearity, it will be a tensor of higher order. So when you consider linear, it is a linear material, then it is a scalar constant of the medium. and it represents what is the response of the medium to a applied electric field. This we have seen earlier. This is the definition of a linear material. So please remember these equations. Now, when you have a higher electric field, that is the electric field which is high intensity, or the electric field that is higher than the interatomic electric field. So when we have this kind of response, then the material will behave non-linearly. That means the polarization P, you can write it in terms of a linear term plus a non-linear term, which is P and N. And the non-linear term, you can write it as the summation of this uh, terms, which is consist of epsilon chi into E, and chi is a tensor of second order, third order, and then fourth order. So I think Ananya, you have a doubt. So let me go through your doubts. Question 4 and 7, assignment 12. In question 4, I used the intensity formula as I equal to P by A and got the answer in 10 to the power 8. But the correct option is 10 to the power 4. Could you please solve step by step both the question? Maybe I missed something in calculation and I still didn't get it. Okay. So, okay, let us go through the question first then. Okay, let me solve in this one instead of the page. Assignment 12. Let us see question 4 first. So let me open the question. Please give me 5 minutes so that I can go through the question. A laser beam with a power of 0.5 watt. So power is given to 0.5 watt. Is focused to a spot of 50 micrometer in diameter. So diameter it is given 50 micrometer. The intensity of the laser beam in, what is the intensity in watt per centimeter square at the focus spot. Okay. So, okay, the formula you have used, it is correct. So intensity is nothing but power per unit area. So power is 0.5 watt, and what is the area given? It is pi r square, right? And R will be 25. So let's say 50 into 10 to the minus 6 divided by 2 square. So if you calculate it, how much it will be? So let us calculate directly in the centimeter square because it is asking in centimeter square. So it is in meter. So it were 2. Pi into 4. So let us see. So this is 50 into 10 to the power minus 2 square. How much you will get for this? So let me calculate. So this is 2. This is, let me calculate the whole. It will be 25 into 10 to the minus 3 square, 10 to the minus 6. Yes. So this whole term will come around 0.0252 into 10 to the power 6. So this will be 2.52 into 10 to the power 4 watt per centimeter square. And the answer is 100 centimeter. Okay, got it then. So this thing is clear, and so do I need to go through question 7, or okay, let me solve that also. Question 7. So it's saying for a specific optical fiber communication, the line width of the source channel is 3 nanometer. That is, so it is given delta lambda is 3 nanometer. Dispersion parameter of the fiber is, that is D, is 30 picosecond per kilometer nanometer. Calculate the temporal spread of the signal pulse after propagating a fiber of 50 kilometer. That is, L is given. Then temporal spread in nanosecond. Okay. So D you already know it is I think delta tau divided by L into delta lambda. So this is 30 picosecond per kilometer nanometer. And this is delta tau, it is asking 30 kilometer is given, and 3 nanometer is also given. So delta tau will be this part, let me say. So this will come around 2700 picosecond. So in nanosecond, at what will be? It will be 2.7, right? Is this clear? So question 7. So delta lambda is already given to you. This is 3 nanometer. And dispersion parameter is also in 30 picosecond per kilometer nanometer. So beware of the units, because most of the time students got the right answer, but only in the unit they got the wrong. Beware of the unit. The unit they are asking, you have to calculate in that unit. And L is also given in this part. Only thing is you have to convert the picosecond to nanosecond. Please go through the answer. If you have any doubt in the steps, you can ask. Okay, so then let me go through the concept that we have left. So we're discussing about what are the linearity and the non-linearity term. So whenever we have a high electric field, so the polarization vector can be written as a summation of a linear term and a sum or a non-linear term. And chi2 by 2 means it is second order susceptibility, chi3 means it is third order susceptibility. And we'll see depending on the order of susceptibility, we'll see different types of nonlinear phenomena inside the crystal. And for, let's say you want to write PNL2, that is the nonlinear term for second order susceptibility, then it will be epsilon 0 chi2 e square. So this is chi2 nonlinear effect. And for chi3, it will be PNL 3 equal to epsilon 0 chi3 into is, it should be EQ, not E square. It's written here, but there is a typo here. So this is chi3 nonlinear effect. So we'll see how this laser comes into the picture of this nonlinear optics. Okay. So let us see what are the orders of chi1, chi2 and chi3 first. So chi1, it is on the order of 1, that is order of 0, 10 to the 0. And chi2, it is on the order of 10 to the minus 12 meter per volt. And chi3, it is on the order of 10 to the minus 25 meter per volt square. And the second in or if you see these terms, this indicates that the second and the third order terms will become significant only when the electric field is greater than 10 to the 4 to 10 to the 6 volt per meter. So only when the the source you are using have electric field in this range, has a magnitude that have electric field in the range, only then you will see the nonlinear effect in the crystal. So let us calculate what is the electric field associated with a laser beam. So this is the expression for the monochromatic electromagnetic wave, E equal to E0 cos omega t. And the corresponding magnetic field, you can write it as a H equal to S0 cos omega t. And to find out the electric field, you have to calculate what is the intensity, and from that you can calculate what is the electric field, magnitude of the electric field associated with the laser beam. So intensity, it is given by n by 2 c mu 0 e0 square. So this you have derived using the Poynting vector formula, that is S equal to E cross H. So this is the fundamental relation between the Poynting vector and the magnitude of the electric field and the magnitude of the magnetic field. And if you equate this expression to the expression P by A, then what we'll see? You see that E0 square can be, you can write E0 square as 2C mu 0 P by A divided by N. And if you take one example to find out what is the electric field associated with the laser, then let us take a 10 milliwatt laser beam of diameter 1 millimeter. Then the E0 square, you can write it as a 2 into C, you already know it is 3 into 10 to the 8 meter per second. Mu 0 is mu 0 is 4 pi into 10 to the minus 7, and N is 1.5. So from that, if you put the values, that is what is the value of P, what is the value of A, then you can easily see the electric field is in the order of 2.5 into 10 to the 3 for a 1 millimeter spot size. Now, if you reduce the spot size, that is, you are focusing the laser beam to a smaller cross section, then you can see how the intensity is getting increased. when you when you decrease the focus spot size from 100 micrometer to 1 micrometer. And for 1 micrometer, you can see how strong the electric field is. 2.5 into 10 to the 6 volt per meter. So it is in the order of, or it is greater than the interatomic electric field. So only when this electric field are comparable, only then the nonlinear effect will start to happen inside the crystal. So let us calculate what is the electric field associated with the medium, that is the interatomic electric field. Then if you take a hydrogen atom, then the Bohr radius it is given by 0.53 angstrom. And the electric field you can calculate it as E equal to 1 by 4 pi epsilon naught Q by R square. So if you put the value of Q and R, then the electric field will come in the order of 10 to the 12 per meter. So you can see this electric field. This is the electric field associated with the hydrogen atom. And if you put the interatomic spacing as a 4 angstrom, then the electric field is in the order of 10 to the 10 volt per meter. So this electric field, it is comparable to the electric field of a focused laser beam. So that means nonlinear effect can happen when you use a laser beam. Okay. So okay, Ananya, I will go. So you have any doubt? The formula you used for D, could you point out in the lecture slide where it is? I couldn't find it in the lecture notes. It's there in the slides. So if I recall, so let me go through. If you want, then let me tell where is it. It's there in the slides also, and it is also discussed in the during the lectures also. Lectures. Okay, I have it. Optical fiber signal transmission, signal communication. Yes, this slide. If you see, this is the dispersion parameter D. Let me erase it. So this is asked in the question 7 regarding the dispersion parameter. So let us go through the next concept. So as I said, please feel free to ask me or stop me anytime to ask your doubts. So it's the interaction section, so it's not required to go through the slides once and you ask the doubt. So you please feel to ask the doubt. Okay. So we're discussing the nonlinear effect. The polarization, it is given by a linear term and a nonlinear term. And when you plot a graph between the P and electric field, linear effect, it will be a straight line. But for a nonlinear effect, we'll see after some electric field strength, the polarization will behave non-linearly with respect to the incident electric field. And this you can take this as chi is the linear susceptibility, you already know. And chi2, it is the second order susceptibility. And what are the phenomena that happens because of second order susceptibility? One is single harmonic generation, some frequency generation, and difference frequency generation. So please remember this, the phenomena, because question may be asked because it's a simple MCQ questions. And chi3, you will see these are the nonlinear phenomena that you can see for the chi3 effect. And chi4, you will see this nonlinear phenomena because of the chi4. Okay. So second harmonic generation, as we have seen, when you pump the system with a frequency omega, then because of the incident electric field strength and because of the comparability between the incident electric field and the laser beam, we'll see there will be a response around 2 omega, and there will be also a response. Omega response will be there, but we'll see a new response around 2 omega. So this is what we mean by second harmonic generation. That is omega, when you pump it, then you will see a 2 omega response also. Please provide lecture slides of week 11 and week 12. Um, so have you checked the Google Drive site of mine? So I think I have uploaded up to week 12, sorry, week 11. If I'm not wrong, I have already set the slides, the lecture slides. Yes, all the lecture slides are there in the Google Drive link. It's available on portal. If you are not able to find in the portal, then please visit my Google Drive link. All the slides are there in the Drive link. So you will see a folder named lecture slides. There I have uploaded all the lecture slides for this course. Okay. Like if question comes like this, will this formula be provided during the exam or we need to recall it? Okay, so these are small relation. It's not like it's a big equation. Only when the it's needed uh, for that is the equation is really long. So only then only the equation will be provided, but I don't think they will provide any equation because they are not going to ask about any write this equation, or they will just ask fundamental question like so based on the small equation they will ask, and whenever it is needed they will provide the equation. But please remember, so depending on, so you have solved the assignment now, all the weekly assignments. So just go through the weekly assignment, what are the formulas that are needed, and this relation, that is dispersion parameter, I don't think it will be provided, so you have to remember it. Just remember how the D is related to temporal spread. It is directly proportional to delta tau, inversely proportional to length, and inversely proportional to the source line width. So it won't be provided in the exam. So I think this clarifies your doubt. Okay. So if not, please feel free to write in the chat box. Let me go through the next part. So the next thing is that we have seen is the sum frequency generation. That is when you pump the system using omega 1 and omega 2, then we will see a response which is sum of this two frequency. That is omega 1 plus omega 2. And optical parametric fluorescence. So please remember this phenomena. That is what happens when you pump a system using this omega 1, omega 2. What will happen if you have a some frequency generation? Okay. And the last is the optical parametric fluorescence, where if you incident omega 3, then you will see a response around omega 1 and omega 2. This is optical parametric fluorescence. And in detail, we have seen how the second harmonic generation is created and what is the condition, what is the requirement for observing such phenomena. So second harmonic generation, it's a nonlinear phenomena, And when you incident, so incident a frequency of omega in a switchable nonlinear crystal. So it's not like every crystal will respond in the same way. Different crystal have different optical properties. Depending on the optical properties, we will see either of this chi2 effect, chi3 effect, or chi4 effect, or any higher order susceptibility. So for the crystal where we see second harmonic generation, when you put a pump of frequency omega, you will see a response around 2 omega as well as some remaining part of the pump in the output. And the condition that is required for efficient second harmonic generation is, first is the phase matching condition between the interacting waves, and second is the good overlap between the interacting waves. So phase matching, what do you mean by phase matching? So phase matching means the phase velocity of these interacting waves, they should match with each other so that they will have efficient interaction. And overlapping, so if is said in the literature, sorry, in the lecture, so if two waves are like this, one is like this and one is like this, then interaction here is much less than the interaction where the two waves propagate in the same direction along the same line. So let us see how we can quantify the efficiency of second harmonic generation. So um, this is the relation, that is the growth of this relation. You don't have to remember this, these are not required for the exam. You just have to remember what is the final output, what is the final relation, and what is the qualitative and quantitative relation. Okay, these are not required. But for your um, study purpose, this has been shown in the slide. So DE2 by DZ. DE2 means the electric field associated with the 2 omega frequency, and E1 is the electric field associated with the omega frequency. So this is the relation how the second harmonic generation, amplitude of the second harmonic generation electric field, it is varying with respect to the propagation distance z. And you can see there is a exponential term here, which is given by e to power I delta kz. And so this indicates that if delta k means k2 minus 2k1, that is the difference between the phase velocity of this original frequency and the second harmonic generation frequency. And in terms of refractive index, you can write it as this, which is 2 omega by c, n2 minus n1. So please remember, n2 means the refractive index at frequency 2 omega, n1 means the refractive index at frequency omega. And this delta k, this is the quantification of the phase mismatch condition. So if it is 0, then we'll see efficient interaction, and if it is not 0, then we'll not see any efficient interaction. The interaction will be not that efficient. And to quantify it, there is one conversion efficiency, eta, which is given by what is the power that is that you got in the output at frequency 2 omega, and what is the power of the input pump power omega. And if you put all the expression, we'll see there are four dependents. One is alpha, others are constant. So if you see the alpha term, alpha is a nonlinear coefficient which is given by half epsilon 0 chi 2. So it directly proportional to alpha square, that is it is directly proportional to the chi 2 square. So the higher the chi 2, higher will be the conversion efficiency. That is, you will get more power of this nonlinear, sorry, of this second harmonic generation frequency 2 omega. And other nonlinear, other dependencies, the propagation constant, that is z. It depends on the second power of the z. And one is the intensity. It is directly proportional to the intensity of the pump. that is P1 by A, and it has a sinc function sine beta by beta square, where beta is, if you write beta, it will be half delta K Z. Okay. So if you plot this sinc function, it will be this we have already seen in the. So if you recall single slit diffraction, you will get a distribution of intensity like this, and the intensity will be maximum only when the beta is 0. So that means delta K is 0. So this indicates only when the delta K is 0, that is only when there is no phase mismatch, we can see the conversion efficiency is high and there will be a efficient interaction that will happen inside the material you are talking about. So this is the graph between the conversion efficiency between different condition, under different condition. One is the phase mass condition, one is the non-phase mass condition, one is the first order quasi-phase. So if you see the phase matching condition, so when delta K is 0, so it will be behave like a z square. So you will see a parabolic curve here. That is why you see a parabolic curve here. But when there is no phase mismatch, when there is a phase mismatch, that means the sine beta by beta is uh the delta, the beta is not equal to 0 here. So because of this sinc function, you will see oscillation like conversion efficiency here. But this conversion efficiency is not high because of the phase mismatch happening inside the crystal. So now let us see how we can achieve this phase match condition. So there are two methods. One is the birefringent phase matching, one is the quasi phase matching. And this first order QPM, it is related to this quasi phase matching condition. So let us see one by one. 1 minute. So when you consider a so for mismatch, phase matching, what we need delta K should be 0. So that means we need delta N, that is N2 minus N1, it should be 0. But when you consider a normal material, then the refractive index at 2 omega not equal to the refractive index at omega, because normal materials they are dispersive. The refractive index will change with respect to the wavelength of the incident light. So a different wavelength, we will have different refractive index. So for this, what we can do, we use a medium where there are two types of refractive index. From that, you can easily match the refractive index at one of the frequency. So these materials are known as the birefringent material. This has two refractive index. One is one is for ordinary waves and one is for the extraordinary waves. Okay. So you can see this phase matching condition. So this is the phase velocity of the ordinary wave. And when you have a extraordinary wave, which is magnitude of this length in the same direction, then you can see this phase velocity will easily match with each other. Okay, so let us see how you can achieve that. So birefringent material, so there are two refractive index. So depending on that, we can plot refractive index surfaces according to the direction of the propagation. We have different type of crystal which show this kind of behavior. One is the uniaxial crystal. So this indicates the refractive index depends on the direction of the propagation. So there are two, one is N0, one is Ne. extraordinary refractive index and ordinary refractive index. This depends on the direction of the propagation, and this N0, it doesn't depend on the direction of the propagation. So that is why if you plot the index surface for N0, you will see a circle for the ordinary refractive index. Okay, that means the refractive index is same in all the direction. But when you plot the index surface for NE, that is the extraordinary refractive index, we'll see this will be ellipse. So that means this ellipse have different magnitude in different direction. Here it will be of one magnitude. Here this in this direction it will be of another magnitude. But if the light propagate in this direction, it will be different than the previous direction. So depending on the direction of propagation, the NE will vary. So that is why we'll see ellipse for the extraordinary refractive index. Now let us say inside this crystal, inside this uniaxial crystal, we incident the light in this direction, which makes angle theta m with the optics axis. So this is the direction of propagation. Now if you see, so this circle means the refractive index, ordinary refractive index at 2 omega, and the inner circle means the ordinary refractive index at omega. Outer ellipse means the extraordinary refractive index at 2 omega, and inner ellipse is extraordinary refractive index at omega. Because we have seen, depending on the omega value, the refractive index will change inside the medium. But if you see the point here, so let me take a different color. So this point, at this point, you can see the ellipse and circles, they are overlapping with each other. So that means this point is when we have same value of refractive index. One is for ellipse, let's say 2 omega, and one is for the ordinary refractive index at omega. So this means if you take a birefringent crystal, then you can achieve the phase matching condition that is required for efficient interaction. So this is already explained in this paragraphs. So the second condition is quasi-phase matching condition. That is compensating a phase matching by periodic modulation of the nonlinear coefficient D. So if you see this diagram, there is a periodic modulation of the index. In this case, it is, let's say, positive. In this case, it is negatives, and there is a periodic modulation. And using this periodic modulation, you can match the phase between the phase velocity of frequency omega and phase velocity of frequency 2 omega. And what is the condition? This is the phase matching condition in case of quasi-phase matching condition. That is 2 times of k at omega plus the wave vector k, which is 2 pi by, let's say it is lambda, equal to k times k phase velocity at 2 omega. Okay. So this we have already seen. This is second harmonic generation relation, and this is the phase matching condition. And this nonlinear coefficient periodic modulation, it is usually happening in ferroelectric domains. By using a electric field, you can modulate the nonlinear coefficient. Okay. And for first order QPM, you will see a response. This will be parabolic, but there will be oscillation because of the sine beta by beta terms. And these are the examples of this QPM materials, periodically poled lithium niobate. So just go through what are the materials. It's a ferroelectric material, and it has a large non-linear coefficient D33, and it is transparent. in the 0.4 to 4.5 micrometer region. This is the definition of periodic pooling. Okay, inverting the ferroelectric domains periodically to match the phase velocity at omega and at frequency to omega. So this is the experimental schematic for single harmonic generation PPLM. So you put the nonlinear crystal inside this micro oven and pass through the pump 1064 nanometer, and you can see this is lambda, this is lambda by 2. So you are getting a nonlinear second harmonic generation because of the PPLM material. So this is the experimental setup where they changed the two parameters. One is they optimize, one is angle and one is the temperature tuning. So depending on the angle as well as temperature, the efficient interaction will also change. So we'll see. This is the angle tuning curve. So by changing the angle, you can see how the second harmonic generation power is changing. And for the temperature, also you can see how the second harmonic generation power, it is varying in this manner depending on the temperature of the system. So these are some experimental plots. And this you have to just go through the materials. What are the names of the material? One is lithium niobate, lithium beta barium borate, ZFP means zinc germanium phosphide, potassium dihydrogen phosphide, potassium titanyl phosphate, and LBO, lithium boron oxide. So to to see the nonlinear effect, what you have to do, you have to put the nonlinear crystal inside the cavity, because only inside the cavity the intensity of the laser beam is high. If you recall, only the I think let's say 90. This is not perfectly reflecting. Some part of the laser beam will pass through this mirror. So this intensity of this laser beam is not that maximum. But when you put the nonlinear crystal inside this cavity, then there will be there is a possibility of observing the nonlinear effect, because the intensity of the laser beam is high inside the cavity. And we have seen also using X-fold cavity, you can integrate various optical components inside this DPSS diode pumped solid state NDI laser. Sorry, ND YBO for laser. So in this case, we can put the nonlinear crystal here. So you can see there will be a second harmonic generation in this direction. Okay. So this is the summary of the effect of how you can observe nonlinear effect inside using a laser beam. So because of the high intensity property of the laser beam, you can see nonlinear effect. There are different types of nonlinear effect, Chi2, Chi3, Chi4, and depending on the order of the susceptibility, you will see different types of nonlinear effect, maybe second harmonic generation, some frequency generation for Chi2, and other higher order optical phenomena for the higher order susceptibility. And we have seen what are the conditions required for achieving such efficient nonlinear effect inside a nonlinear crystal when you put a laser beam. So this we have seen the phase matching condition is required, and good overlap between the interacting wave is also required. And we have seen second harmonic generation, and we can use intracavity SSG to get a second harmonic generation response. Okay. Now we'll talk about the final part of this week, that is laser safety. After that, we'll solve few problems. So laser safety, it depends on the safety of the device, that is the laser you are using, and the person you are using, the person who is using the laser. So based on the output pump power level, uh, you can classify the laser into different category. It may be a class 1 laser, it may be a class 2 laser, or class 3, class 4. So it depends on the pump power level of the laser. So actual power level, it depends on the laser wavelength, the mode of operation, that is whether it is a continuous wave or it is a pulse laser beam, or what is up to what time you are exposing the laser beam or you are using the laser beam. So class 1 laser, these are safe laser. This is power in the order of 10 microwatt. Class 2 laser, this has power which is less than 1 milliwatt, and it has power in the order of 100 microwatt. So as the class increases, the power level of the laser increases. And according to that, the safety precaution will also increase. So class 3 laser, it can be this is sub-classified into two types. One is class 3A and another one is class 3B. And if you look at it, the class 3A, it has power in the order of 1 to 10 milliwatt. And these are safe to handle and work with, but don't look at the laser directly because the high intensity will damage the retina. So that is why it is advised that don't look at the laser directly through your eyes. And class 3V laser, it has power in the order of 10 to 100 milliwatt. And these are worked with caution, and same exposure of eye is avoided, skin of or skin to the laser beam, or including the scattered as well as the incident beam. You have to avoid the directly looking at the laser. So for that, you should use goggles or high reflect to avoid the damage the power of the laser beam. And class 4 laser, it is a high power of in the order of 1 watt, or it can be higher than this value. And this is typically used with extra caution because it is high power. So we must use safety eyewear goggles of suitable optical density, and high reflection from the metallic surface must be avoided because it is high power. So reflected laser beam will also have high intensity. And whenever this is operated, it is advised that the blinking red light and the door interlocking mechanism must be. So this phenomenon is already explained during the lecture. So now let us see what is OD. So OD means optical density. So it indicates how much how much power can be attenuated by using a goggles of specific optical density. So if you define what is the optical density, so this is given by OD equal to minus log 10 P transmitted divided by P incident. So, and you can also write it as a 10 log 10 P incident by divided by P transmitted. So let us take you have a OD of 5. So that means 5 equal to log 10 P incident divided by P transmitted. And if you remove the log, then P incident by P transmitted will be 10 to the 5. So that means P transmitted will be 10 to the 5 lower than the P incident. So this is what we mean by optical density. So higher the optical density, higher will be the attenuation power of the goggles. So when you use class 4 laser, then you will use goggles of higher optical density. So these are some examples. Let's say you have optical density of 0, that is you are not using any goggles, then there will be 100% transmission of the laser beam and there will be 0% attenuation. And if you have a goggles of optical density 1, then there will be 10% transmission and 90% attenuation. And as you decrease as you increase the OD, the transmission will decrease, and according to that, the attenuation by the goggles it will increase. Okay, so this is it is clearly shown in this figure. So if you look at this figure, so this is the plot between the lambda and the attenuation. And let us say the goggles is operating around the wavelength 1064 nanometer. So that means if you plot the transmission, there will be transmission for the visible wavelength. We'll see, but when it enters the laser region, then the transmission suddenly decreases. So that means it is safe to use the goggles because it is transmission in the visible, but it is attenuation in the for the laser wave. The attenuation, it all depends on the what is the optical density of the used goggles. So these are some precautions that you have to take while using a laser. So various precautionary measure to be followed depending on the type of laser. It can be it. So if it is a type 4 laser, then the safety precaution will be more strict than the type 1 laser, sorry, class 1 laser. And electrical power requirement, operating voltage and current interval, depending on that also the safety will change. And the laser should be protected against any thermal and mechanical shock or any static charges or EST for the semiconductor laser. Okay, so this covers up what is the week 12 content. This summarizes all the things. So we have gone through. So if you summarize, initially we have talked about what is the interaction of radiation with matter. That is, there will be absorption, there will be emission, and the emission will be either it will be a stimulated emission or it will be a spontaneous emission. And we have seen for laser, we need stimulated emission, and there are conditions for the stimulated emission. So before that, we have gone through what are the Einstein coefficient and what are the atomic lines of function, because normally for a transition, for atomic transition, we expect we'll see lines in the spectrum, either emission and absorption spectrum, but we typically see a distribution around some frequency. So this is all due to the atomic lines of function, that is G of nu. And we see what are the conditions for amplification of stimulated emission, and what are the different types of line broadening mechanism, and the laser rate equation. We have solved the laser rate equation for different types of system, let's say 2-level system, or it may be a 3-level system, or laser rate equation for a 4-level system. And finally, we have seen the laser amplifier, different types of laser amplifier, and specifically we have discussed what are the erbium doped fiber amplifier. And in the third part, we have seen what are the resonance frequency of a cavity, how you, so what are the condition for getting a resonance frequency? That is when the round trip phase, it is integral multiple of 2 pi, then you can see there will be resonances that will happen inside the cavity. And what are the spectral response of a optical resonator and different resonator loss, cavity lifetime, and what are the resonator stability condition. And we also discuss what are the ray paths in different types of mirror resonator and also in spherical mirror resonator. And once we studied the basics, the condition required for resonance as well as what are the resonance that will happen inside the cavity. So we studied what are the modes, what are the supported modes inside the cavity. The modes can be a transverse mode. Transverse mode means it specify one type of one type of field distribution that is supported inside this cavity. So whenever this subfield it oscillates inside the cavity, the field distribution remain unchanged. And what are the we have also discussed what are the Gaussian mode, what are the longitudinal modes of a spherical mirror resonator. And in the fourth part, we have seen the laser oscillation and the threshold condition, laser oscillation and the threshold condition, and spectral hole burning, and variation of laser power around the threshold, optimum output coupling, what are the laser output characteristics, and what are the laser beam characteristics, and what is the ultimate line width of the laser. And we have also discussed pulse laser and how we can achieve a pulse laser by using mode locking and Q switching. So these are different methods of getting a pulse laser. And in the last part, we have discussed what are the different types of laser, some common laser, Nd:arc, diode form solid-state laser, fiber laser, semiconductor laser, and what are the different types of laser and amplifier that is used in optical communication, and how you can use laser for studying any non-linearity of a medium, and what are the safety precautions that should be followed while working with laser. Okay, so this summarizes the week 12 content. So I hope whatever I have discussed, this is uh, clear to you. And if not, please feel free to write in the discussion forum, or you can ask your doubt in the discussion forum or now only. So we'll solve few problems now, which is related to week 12. Mm. So these are the doubts that you had for the assignment 12. So let us solve few additional problems. Please read the question once. So let me read out the question for you. So the question says a uniform laser beam of power 50 milliwatt is propagating in free space. If the diameter of the beam is 4 millimeter at a particular position, the amplitude of the electric field is. So this is similar to one of the problem of assignment 12. So let us see what is given to us. So first thing that is given is uniform laser beam of power 50 milliwatt, and it is propagating in free space. That means what will be the refractive index? It will be 1. So please go through the question. Whenever you are solving the question, please go through the question clearly so that you are clear that what is already given to me and what I need to find out. And the next thing that is given is the diameter of the beam. It is the beam diameter. It is 4 millimeter at particular position. Then what is the electric field in volt per meter? So you know the relation intensity. It is given by if I so there is a relation that is given. I think it was paid. This relation. So you can say there is a relation between the intensity and E zero square, and C mu zero are constant. You already know what are the values of C and mu zero. N is already given. It is said that it is propagating in the free space. That means N equal to 1. So let us put the values. So intensity it is given by So this is n divided by 2c mu 0 e 0 square. And you already know the intensity is given by power per unit area. This is equal to n to c mu 0 e 0 square. So to find out what is the value of electric field, you have to rearrange the terms. So P by A to C mu 0 divided by M. And these are all given. Power is given, it is 50 milliwatt. And the minus 3 watt to 2. And C is 3 into 10 to the 8 meter per second. Mu 0, you already know it is 4 pi into 10 to the minus 7 divided by area. So area will be pi r square, right? And if refractive index is 1 already. R is, which is R? It is 2 mm. So beam diameter is 4 mm, so it will be 2 mm. So that means this is 50 into minus 3, 2 into 3 into 10 to the 8, 4 pi into 10 to the minus 7, I 2 into 10 to the minus 3 square. So if you solve it, you will get a value around. So this pi will cancel. So this is 100. That means this is 3 into 10 to the 7. There is minus 7 here, and this is 4 into 10 to the minus 6. So this is E0 square. Okay, so there is a 4 here, right? 4 pi. So this 4 is also here, so this will cancel. So this final is 3 into 10 to the 6 for E0 square. And if you calculate E0, then that will be root over 3 into 10 to the 3 volt per meter. So this is 1.732 into 10 to the 3 volt per meter. So this will be the answer for this question. Let us move to our next problem. So the second problem is, it is recommended to have a minimum optical density OD of 5 for a laser safety glasses to handle a erbium doped fiber laser with continuous wave output power of 1 watt. Accordingly, the OD required for laser safety glasses for handling a high power erbium doped laser giving continuous wave output of 5 kilowatt is. So the recommended OD is given, the minimum optical density. So it is given output power output power is 1 watt and OD is minimum optical density OD is 5. So what is the relation between optical power density and the output power? So if you go through the slides, it will be 10 log P in by P out. So if I'm not wrong, that is the relation. So D, I think we have discussed in log 10 P in by P trans. So you have to use this relation to find out what is the minimum optical density required for a high power erbium doped laser. So what is given? That means log 10 P in divided by P transmitted equal to 5. So you can calculate the transmitted power from here. What is the minimum transmitted power for laser safety for a 1 watt laser beam? So the power transmitted should be P in divided by 10 to the power 5. That means the after using the goggles, the transmitted power through the goggles, it should reduce by 10 to the power when you are using 1 watt. Now for a 5 kilowatt, you can see how intense, how much power this erbium doped laser has. So this is given for next part, erbium doped laser. It is a P out of 5 kilowatt. So that means this will be the P in for the goggles. So P in equal to 5 kilowatt for the goggles. So now we want the power to reduce by 10 to the power 5. So that means P out, it should reduce by 5 by 10 to the power 5. Sorry, it should reduce to 1 by, sorry, there is a typo. This is 1 divided by 10 to the power 5. So we want the output power through the goggles. It should be 1 by 10 to the power 5. So that we are in the safe region. So that means OD will be log 10 P in by P out. So log 10 P in is 5 kilowatt and P out is 1 to 10 to the power 5. This was in terms of watt, right? 1 by 10 to the power 5 watt. So that means if you omit the kilowatt, it will be 10 to the power 3. And if you calculate it, 5 into 10 to the power 8. So if you calculate it, it will come around 8.7. So that means for this high power erbium doped fiber, so you have to use a goggles which has optical density of 9 or greater than 8.7. Okay. So this is the answer. So let us move to the next question. So the next problem is, let's go through the question once. So it is similar to one of the problem of assignment 12, right? So the question says, let me read out for you. Estimate the temporal spread of an impulse in a single mode optical fiber communication system with a fiber length of 40 km. So it is asking to find out the temporal spread, uh, and you are using a single mode optical fiber which has a length of 40 km. And it is also given that the dispersion parameter of the fiber is 25 picosecond per kilometer nanometer. Okay. And the line width of the source, that is the channel width, it is also given. It is a 0.1 nanometer. And it is asking about if you incident the laser beam in this single mode operation, then what will be the spreading in time when you record the laser output in the other end. So if you recall, when you incident a laser source of chase line with delta lambda, the output when after going through a fiber, let's say this is the fiber, then you will see there will be a decrease in amplitude and there will be a, so the decrease in amplitude, it is attenuation, and the spreading, it is due to the dispersion. So this is what we mean by temporal spreading. So let us see what is given to us. So fiber length is given. Fiber length L is 40 kilometer and dispersion parameter is given. That is D equal to 25 picosecond per kilometer nanometer. And the line width is also given. That is all the parameters is already given. You just need to put in the equation and find out what is the temporal spreading. And as we have seen, D, the dispersion parameter, it is directly proportional to delta, the temporal spreading, delta tau, inversely proportional to the length of the optical fiber and inversely proportional to the source line width. Now you just have to put the parameter. So it is 25 picosecond. So be aware of the units. So please, while going through the calculation, remember the units you are taking. Delta tau it is asking. And L is, it is given 40 kilometer, right? 40. And delta lambda is 0.1 nanometer. There is kilometer here. This will cancel this unit. We will get 4 here. That means delta tau is 100 picosecond. That means it will be 0.1 nanosecond. So the answer will be option D, 0.1 nanosecond. Please go through the question for once. It's a conceptual question. So you have to read each option carefully so that you can figure it out what the question is asking. So the question says, choose the incorrect statement related to second harmonic generation. So we have seen second harmonic generation and what are the condition requirements second harmonic generation. And the question is asking which one of this option is the incorrect statement. So the first one is the larger the nonlinear susceptibility, the larger will be the conversion efficiency. This we have already seen. So if you recall the conversion efficiency, it is eta. Eta is directly proportional to alpha square, that is eta directly proportional to chi2 square. So the larger the nonlinear susceptibility, the larger will be the conversion efficiency. Second option is the larger the interaction length, larger will be the conversion efficiency. This is also correct because interaction length is nothing but the propagation length. So interaction directly proportional to z square. So this is also correct. Option C, the larger the intensity of the pump, the smaller will be the conversion efficiency of SSG, which is not correct. So if you recall, eta is directly proportional to P1 by A, which is nothing but the intensity of the pump. So as you increase the pump intensity, then the conversion efficiency, that is how much incident power will be converted to the power of single harmonic generation. So this will also increase when you increase the pump power. So that means we already got the answer. That is option C. But let us see what does the question option D says. Option D is conversion efficiency of SSG is maximum when the phase velocity at omega is equal to the phase velocity at omega, which is also correct because for efficient interaction, we require the phase velocity at this pump wavelength and the single harmonic generated frequency. They should match. There should not be any phase mismatch. So this is correct. This is for delta k equal to 0. Now let us see what does question 5 says. This is also conceptual. So you have to go through the each concept so that you can solve the problems in second. This is so question 5 says the polarization response of a medium in the presence of an electric field, it is given by P equal to epsilon chi e, which is a linear term, and these are chi2, chi3, these are the non-linear term. So this is the general expression for a polarization response. Now the difference frequency generation is due to which component of the susceptibility? That is DFG. This is due to which non-linear phenomenon? It is either is it because of chi, that is the linear part, or it is because of chi2, chi3 or chi4. So if you recall, this is due to chi. Let me show you. So this is because of kite effect. So this is why I have told you to remember the phenomena, that is optical nonlinear phenomena that happens because of different higher order susceptibility. Their difference frequency generation. So that means answer will be option B. So let us see the next problem. So please go through the question once. So the question says, the ITU, that is the International Telecommunication Union, has set the channel spacing for DWDM communication system as 50 gigahertz. That is, the separation between different channels would be 50 gigahertz. So when a particular network provider opts for an operating wavelength range of 1530 nanometer to 1560 nanometer for optical communication, then what will be the maximum number of DWDM channel that can be passed through this operating wavelength? So for this, what you can do, so you know the relation, right? C equal to frequency into lambda. So that means delta F, mod of delta F, it is C by lambda square into delta lambda. So that means if you want to find out what are the number of channels that can be passed through in this region, what you have to do, you know the channel spacing. Now you have to find out what is the bandwidth of the operating wavelength in the frequency. That is delta F. So you need to calculate what is delta F first. Then when if you divide delta F, that is the bandwidth, let's say this is delta F. Then if you divide, so and channel spacing is already given in terms of hertz. So if you divide delta F, so this is total delta F, let's say, and this is channel spacing. So if you divide this, then you can easily find out what is the number of channels that can be transmitted using this operating wavelength. So delta. So first you need to find out delta F. So this is 3 into 10 to the power 8, and this is delta lambda, that is 30 into 10 to the power minus 9. It's already given. So this we have you can get it from delta lambda. So wavelength range is given, right? So let me write it here clearly. So delta lambda is nothing but lambda 2 minus lambda 1. Lambda 2 is, it is given 1560 minus 1530 nanometer. So this is 30 nanometer. That is 30 into 10 to the minus 9 meter. And lambda, you have to take the average of lambda 1 and lambda 2. So it will come around. So this is 1560, 1530 to 1560. So it will be 1545 nanometer. Now you have everything. So you just have to calculate delta F. So this will be 3 into 10 to the power 8. Lambda square is 1545. 10 to the minus 9 square. And delta lambda is 30 into 10 to the minus 9. And if you calculate it, it will come around 3770.384 gigahertz. Okay. So that means number of channels will be, it will be delta F divided by the channel spacing. So channel spacing in the same unit, that is in hertz only. So delta F, it is given 3770.384 gigahertz and channel spacing is 50 gigahertz. So this will come around 74. That means you can easily pass 74 channel when you have a channel spacing in 50 gigahertz. So answer will be 74. Okay. Now let us move to our next question. It's a conceptual one. Please go through the question once. So the question says, choose the correct statement of erbium doped fiber amplifier. One is it offers the lowest noise figure, which is, it depends on the type of application. And second thing is, so you have to find out what is the best correct statement for the erbium doped fiber amplifier. So please go through the all the options so that you can be sure which one is the appropriate answer. Second option is are switchable for amplification in the mid infrared wavelength region, which is not correct because these are usually used around 1550 nanometer. So this is around near infrared wavelength region. So this option is also not correct. And the third option, it says operates in the wavelength regions where standard single mode fiber have lowest losses, which is correct because standard single mode fiber, they have the lowest losses around 1550 nanometer. So if you recall the loss diagram, different, so we have divided the 1550 into different sub bands, C band, S band, L band. So This means this erbium doped fiber, they operate around the near infrared region. So option C is not correct. Sorry, C is correct because they operate in the fiber. So I got confused in between B and C. So C tells operates in the wavelength region where standard single mode fibers have lowest loss. So standard single mode fiber have lowest loss around 1550 and erbium doped fiber are used around that frequency only. So correct statement is option C. But let us see what is option D. Option D says these are switchable for transparent optical networks since they transmit input signal even when not being pumped, which is not correct. Only when there is a pump wavelength, only when this will work. Okay. So option D is incorrect. So answer will be option C. Okay, so let us move to our next problem. The next problem is it's also a conceptual one. Which one of the following is not a nonlinear optical effect? One is the second harmonic generation. This you already know it is a it's a nonlinear effect, optical effect because of the Chi2 susceptibility. And B is the four-wave mixing. This is also a nonlinear effect. I think this is because of Chi4, I think, right? No, this is because of Chi3, four-wave mixing. So this is Chi3 and C option is stimulated emission. This is obvious. This is not a nonlinear optical effect. So that means the answer is option C. And option D is optical parametric amplification, which you already know it is a nonlinear effect. Okay, so let us move to our next problem. Please go through the question once. It's a numerical problem. If you know the relation, then you can easily find out what will be the answer for this question. So the question says, given that the average output power of an optical transmitter is 10 watt, what is the equivalent output power in dBm? So you have to express the output power instead of watt, you have to express it in terms of dBm. So if you recall, there is a relation convert watt to dB, converting output power from watts to dBm. So power dBm is given by 30 plus 10 into log 10 power in watt. And this is already given power in watt. So that means this is 30 plus 10 log 10 power in watt is 10. So this will be 100 log 10 base 10. So this will be 30 plus 10. 40 dBm. So answer will be option D. So let us move to the next problem. This is a conceptual problem. Okay, please go through the question once. So it's a easy question. Uh, it's not that difficult. So the question says which property of laser is responsible for nonlinear effect? So laser has different spatial properties. This we have discussed in our first session. So if you recall, laser has high directionality, it has high monochromaticity, low divergence angle, and high intensity. Now, among this property, which one is responsible for the nonlinear effect? Chi2, Chi3, and Chi4. This you can easily guess. This is because of the high intensity of the laser beam. Okay, this is one of the straightforward question. Now let us move to our next final problem. This will be our last problem. Please go through the question once. Okay, so let me read out the question. So the question says, laser beam is focused to a region A, B, C of diameter 1 millimeter, 100 micrometer, and 1 micrometer, respectively. So you have three different regions A, B, and C. So focused region of laser in this three different region. Here it is 1 millimeter. Here it is 100 micrometer, and here it is 1 micrometer. Then what is the relation between the intensity and conversion efficiency in different regions? So if you first we have to find out what is the relation between intensity. So if you recall, if same laser which is same power and is focused on different region of different diameter. So what is the relation? Intensity is given by power per unit area. So intensity is inversely proportional to A, that is R square. So lower the radius, higher will be the intensity. So if you see, this is 1 mm, this is 100 micrometer, this is 1 micrometer. So that means R A, it is, sorry, R is greater than RB, greater than RC. So that means the intensity of A is less than intensity of B, less than intensity of C. This will be the first relation. And the conversion efficiency, if you recall conversion efficiency eta, it is directly proportional to the intensity, which is P1 by E. So that means higher the intensity of the focus laser beam, higher will be the conversion efficiency. So we have relation of intensity is this IA less than IB less than IC. So that means eta A should be less than eta B is less than eta c. So this is the relation between the conversion efficiency. So that is why you have to remember what is the qualitative and quantitative relation between different parameters, how one parameter is affecting the other parameter. So in nonlinear effect, we have seen there are three important parameters. One is propagation length, other one is the nonlinear coefficient, and one is the intensity, and one is the sinc function. So you have to remember all these qualitative relation, how these are qualitatively related, and depending on that, you can easily find out what is the relation between the intensity at different focus rates. So this summarizes our week 12 content as well as some additional problem related to week 12. So I hope whatever I have discussed in all of this week, starting from week 1 to week 12, so we have covered the concept as well as we have gone through the lecture slides. So we have discussed the assignment, weekly assignment that has been floated in the course website. And we have also I have also tried to clarify your doubts. And in addition to that, I have solved few problems that is somewhat similar to assignment, but these problems, some of the problems are quite different from the assignment. So I think whatever I have discussed from week 1 to week 12, these are all clear to you, and these are helpful to you to go through the weekly concept again. And I think whatever I have clarified, whatever doubts you are having, I have tried to clarify your doubts, and these are also understandable to you, whatever doubts, whatever answer I have tried to give you. And we will end the section now. And for the exam, is I have said earlier also, the exam date, it is already given in the course website, and the timing is also given. It's on 3rd November, and there is a morning time and evening time. So please go through the course website for the exam details and all, and what are the percentages. And regarding exam pattern, we have already discussed. The exam will be assignment based. Question will be similar to assignment. Some of them will be conceptual, and some will be numerical, and some will be like fill in the blank question, and you will be asked to fill up to certain decimal. So that is all about the exam pattern. And regarding the slides and the videos, I think one Google Sheet it is shared with you, where I have mentioned all the link to the live session, and there is a folder in the Google Sheet also, where you can find the extra questions that I have solved or the lecture slides. If you are not able to find out in the course website, you can easily visit the link to find out the lecture slides for this course. So I have uploaded today. I will upload today, or I think today also, today only I will upload the week 12 content. And other than week 12 videos, others are already there in the link, in the Google Drive link. So please visit the link and go through the lecture slides. There is a folder named lecture slide where you can find the lecture slide for this course. And additional questions also I have uploaded in the website. Today I will upload for this note. And all the best for your exam. I hope this live section is helpful to you. Please prepare well. The questions will be easy, and if you go through the all the concept and as well as the slides and the assignment, will be able to easily pass the exam. Okay. So Thank you everyone for joining the session from 4 to 6 every Saturday. I think the section that I have conducted is helpful to you. So I hope the exam will went well. So all the very best for the exam. So let us end the section now then. Goodbye everyone.